Hello! In Arduino Piano Part 4 I will begin with the software. But before I start writing the software, I will explain the data structures which are used in the project. See you after the intro. Today I will show you the different integer formats and then explain what a nibble is and how hex numbers are coded. Then I will give you a detailed description about pointers, how they work, the application of it, and how the pointer arithmetic works. To avoid a too long video, I will put the elements array, struct and union in part 5. Whenever we calculate with numbers, we will use the data types int8t, uint8t, int16t, uint16t, int32t and uint32t. The reason is that these data types are exactly defined. With the original data types like char, int, long, we have especially with the int type an issue because it is very implementation dependent, and this can cause a problem when moving the software to a different microcontroller system. The names are coded as follows. Int stands for signed integer, 8 for 8-bit, and underscore t, that the name is a type name. uint stands for unsigned integer, 8 for 8-bit, and underscore t, that it is a data type name. So we have here a 2-byte signed integer type, here a 2-byte unsigned integer type, here a 4-byte signed integer type, and here a 4-byte unsigned integer type. There are also bigger integer types like int64t or uint64t and so on, but these bigger types are not used in our project. The variable declaration is as follows. We write the data type name and then the variable name and a semicolon. If we want to have a variable with an initial value, then we write the data type name, the variable name, an equal sign, and the initial value and a semicolon. Signed integer numbers are coded as follows. In the highest or leftmost bit, there is a sign bit. A 0 means positive numbers and a 1 means negative numbers. For positive number, we have in the remaining bits here the binary code of the number 0, 1, or for an 8-bit signed integer, the remaining 7 bits are 1 for 127. The negative numbers are written in the 2's complement. 2's complement means we take the positive number, build the complement, which means zeros become 1 and 1s become 0, and then we add 1. For example, -1, we take the positive 1, make all the zeros to 1 and this 1 to 0. Then we have 1, 1, 1, 1, 1, and here a 0, and now we add 1, and we can become here also a 1, and then we have the -1. Or for -127, we take the positive 127, it's a 0 with a lot of 1s here, then we pick the complement and we get 1 and all the others are 0, and finally we have to add 1 and we get 1 zeros and at this position a 1. In general, for 2 complements signed integer type, we can say the -1 is always all bits are set to 1, and the biggest negative number is the sign bit is set and all the other bits are 0. For unsigned integer, all the bits are used to represent the number here in a binary code. So we have here 0, 1, and for an unsigned 8-bit integer, all 8 bits are set to 1 for the number 255. Here a summary of the different integer data types with the related minimum and maximum value. At big integer numbers, the long queues of zeros and ones become difficult to read and write. So groups of 4 bits are combined to so-called nibbles, and nibbles are represented by hex numbers. We have here the binary code, and here's the hex value. The hex numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. Here some examples for 16-bit signed integer values. 0 is all bits 0, so all hex numbers are 0. -1 is all bits Z, so all hex numbers are F, 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 F. 1 is also easy. All upper nibbles are 0 and the least significant nibble is 1. The most positive number is the sign bit is 0 and all other bits are set to 1. The dual number of hex 7 is 0111, so the sign bit is 0 and the remaining bits are 1s, and F is 4 times 1, so we have here all 1s. The most negative number is the sign bit is Z and all the remaining bits are 0. The dual code of hex 8 is 1 and 3 times 0, 0, 0, and 0 is 4 times 0, so we have the most negative number here. To enable the C compiler to distinguish between hex numbers and decimal numbers, all hex numbers begin with a 0x. For example, 8000 hex is written as 0x 8000. Now to the program code. These 3 macros I have defined to shorten the program code that it fits in the video description below this video. The macro stop is an endless loop do while true to stop the program execution. The print macro will be replaced by serial.print and the println macro will be replaced by the serial.println. In the setup routine, we open the serial channel to communicate with the monitor program. The selected baud rate in the monitor program must fit to the selected bitrate here. With a small test program, we'll display the minimum and maximum values for the different integer data types. The maximum value for an unsigned integer is when all bits are set or when all nibbles are set to F. The maximum number for a signed integer is when the sign bit is 0 and all the remaining bits are set, or the most significant nibble is 7 and all the remaining nibbles are F. The most negative number of signed integer is when the sign bit is set and the remaining bits are set to 0, or the most significant nibble is 8 and all the remaining nibbles are 0. For the other integer types it's the same, only with less digits. For each data type and extreme value we have defined here a variable and initialized with its related value. Here we print the headline and then all the variables with its related information text, and after that we stop the program execution. And in the main program we start the subroutine data size test. Now we'll go back to the subroutine here and upload the program. We print here the headline data size test and see here the headline data size test. Then we print int 8t min and the value of int 8 min, and we see here int 8t min and the value of the variable, and we go on until print uint32t max and the value of uint32 max. And we have here uint32 max and its value, and then we stop the program execution. We have here our integer data types, and here the minimum and maximum numbers in decimal representation. Pointers are a very powerful tool in C and C++. They are necessary in C to transfer data from a subprogram to the calling program via parameter. In C++ there is a more elegant way to do this. Another big field of application is to build up complex data structures like linked lists or data trees. Also, it is possible to have free access to any subpart of bigger data structures via pointers. For our exercise, we will do some variable declarations. An 16-bit integer variable a, an 16-bit integer variable b, and a pointer c to a 16-bit integer variable. With the asterisk, it is indicated that the variable c is a pointer variable. With an unsigned before a variable name, we will get the address of the variable. With an asterisk before a pointer variable, we will get access to the content of a memory location to which the pointer points. These two are valid for execution code, not for declaration. Now an example for execution code. With the statement a is equal hexadecimal 2211, we load the number 2211 into the variable a, and the variable a has two memory places. It's 0114 and 0115. These are fictive numbers. In your real systems here we can have any other address, but it is important that the numbers are increasing. With the statement c is equal and a, we load the address of a into the memory location of c. So we have 0114 is 0114 in c. The address is always the first byte if we have data structures which have more than one byte. With the statement b is equal asterisk c, the content of the memory location to which c points will be loaded into b. C points to 0114, and in 0114 in the memory location we have 2211 hex, and we load it into b 2211 hex. With the statement asterisk c is 0, we write a 0 to the memory location where c is pointing to. C is pointing to 0114. Here we have the memory location 0114, and we write a 0 to the memory location 0114. What we get with these statements is that with asterisk c we get access to the same memory locations and operations as we write a directly. I activate pointer test1 in the main loop and go to the subroutine to see the code we just discussed. I upload the code to the Arduino, that we have the possibility to compare the code and the output on the monitor. Here our variable declaration. We have a 16-bit integer variable a, a 16-bit integer variable b, and a pointer variable c, which points to a 16-bit variable. Here we output the headline pointer test1 to the monitor and see here pointer test1. We load the hex value 2211 into the variable a and send the message a equal to the monitor and send the 16-bit value in hex format of the variable a. And we see a equal is our message and the hex value 2211. Now we load the address of variable a into the pointer variable c and output to the monitor the message c equal and the 16-bit value in hex format of the variable c And here we must do a type conversion because address is not compatible to a normal 16-bit number without type conversion. And then we send the message asterisk C equal and then the 16-bit value in hex format of the variable to which C is pointing. And we see on the monitor here C equal 08FA, which is the address of variable A, and then the contents of the variable where C is pointing to 2211. Now we load the contents where the variable C is pointing to into the variable B and write the message B equal to the monitor and then the 16-bit value in hex format of the variable B. And we see B equal 2211 in hex format. Finally, we load the value 0 to the location where C is pointing to and output on the monitor asterisk C equal and then the 16-bit value in hex format of the location where C is pointing to and also the message A equal and the 16-bit value in hex format of the variable A. And we see asterisk C equals 0 and A equals 0. So every time when we have access to asterisk C, in reality we work with the variable A. Now I want to show how to have access to a part of a bigger variable structure via pointer and how the pointer arithmetic works. We define a 32-bit integer variable A and a pointer variable which points to an 8-bit integer variable. First we load the hex value 44332211 into the variable A and send the contents to the monitor, and we will get 44332211. Then we load the address of the variable A into the pointer variable C. The address of the variable A is the first byte of A and has the address 0114, and we load this in the variable C 0114. An address or pointer to a 32-bit variable is usually not compatible to a pointer of an 8-bit variable. To tell the compiler that it is our intention, we have to do a type conversion here. Now we have access to the 8-bit variable to which C is pointing. C is pointing to 0114 and at the address 0114 the contents of the memory is the hex value 11. Now we increase the pointer C by 1 and C is pointing now to 0115. Now we output the 8-bit variable where C is pointing to. C is pointing to 0115 and at the location 0115 we have the hex value 22. Again we increase the pointer C and get 0116 in C, and then we output the value where C is pointing to. C points to 0116 and at the memory location 0116 we have the hex value 33. We increase the pointer C again and output the value where C is pointing to. C points to 0117 and at memory location 0117 we have the hex value 44. We have now activated pointer test2 in the main loop and go up to the subprogram pointer test2. I will upload it now to the Arduino that we can compare the output on the screen and the program code. Here we have the declaration of our 32-bit integer variable A and the pointer which points to the 8-bit integer variable. First we print the headline pointer test2 and we see on the monitor pointer test2. Then we load the hex value 44332211 into the variable a and output the message a equal and the 32-bit integer value in hex format of the variable a. And we see a equal 44332211. Then we load the address of variable a with type conversion into the pointer variable c. We output the message c equal and the 16-bit value in hex format of the pointer variable and the message asterisk c equal and the 8-bit value in hex format of the variable where c is pointing to. And we get c equal 08EC, which is the address of the variable a, and asterisk c equal 11, which is the lowest byte of the variable a. Now we increase the pointer c by 1 and output c equal and the 16-bit value in hex format of the pointer variable c, which is the address, and asterisk c equal and the 8-bit value in hex format of the variable where c is pointing to. And we do this 3 times. And we see on the monitor that the address is increasing C, D, E, F, and the variable where c is pointing to is in the first step 11, the lowest byte, in the second step 22, the second byte, the third step 33, third byte, and in the last step 44, the fourth byte. And now we want to look what happens when we use a pointer to a 16-bit integer variable instead of a pointer to an 8-bit integer variable, and how the pointer arithmetic changes. And again we load the hex value 44332211 into the variable a and output it to the monitor. Then the memory looks like this, and we get on the monitor 44332211. Now we load the address of variable a into the pointer variable c. The address of variable a is the first address of the variable a, it's 0114, and we load it to the variable c 0114. C is a pointer to a 16-bit integer, therefore we need to do here a type conversion to a 16-bit integer pointer. And C has 2 consequences. The first effect is that C points now to a 16-bit integer instead to an 8-bit integer. So every access to asterisk C is now to 2 bytes instead to 1 byte. And we get here the output of 2211 hex. The second effect is that when we increase the pointer by 1, it moves not 1 byte, it moves by one 16-bit integer variable, which is 2 bytes. We see it here, we were 14 and now we are 16, and 16 is 2 bytes further. And on the next output we get the variable where C is pointing to, and this variable is a 16-bit variable, so we get 4433. So we can summarize: the pointer arithmetic is automatically adapted to the data type to which the pointer points. When we increase the pointer by 1, it is automatically moved by so many bytes which are necessary for the data type to which the pointer points. When we increase the pointer by 2, it is automatically moved by twice of the bytes which are necessary for the data type to which the pointer points, and so on. I have now activated pointer test 3 in the main loop and go up to the pointer test 3. Now I load it up to the Arduino board that we again can step by step compare the program code and the output on the screen. We declare a 32-bit integer variable a and a pointer c which points to a 16-bit integer variable. And then we output the headline pointer test 3 to the monitor and get pointer test 3. Again, we load the hex value 44332211 into the variable a and output a equal and the 32 integer value of in hex format of the variable a, and we see a equal 44332211. And now we load the address of variable a converted to a pointer to a 16-bit variable into the pointer variable c. We output now c equal and the 16-bit value in hex format of the pointer c, and then we output asterisk c equal and the 16-bit value in hex format of the variable where c is pointing to. And we see on the screen c equal 08FO, which is the address of the variable a, and the contents where c is pointing to is 2211, which are the lower 2 bytes of the variable a, 2211. Now we increase the pointer c by 1 and output again the address, which is c, and the contents where c is pointing to, and we get the address is 08F2, which is 2 bigger than the address before because we have moved by one 16-bit integer value, which is 2 bytes. And the contents where c is pointing to is now 4433, and 4433 are the 2 upper bytes of the variable a. And if we write instead of c is c plus 1 simple c plus plus, then we will get the same output. I load it up to the Arduino board, and we see we have here the address F0 and here the address F2. It's an increase of 2 bytes, and here we have only an increment of 1. And here we have the 2 lower bytes, and here we have the 2 upper bytes. And now we want to see what happens with a bigger step width. I write c is c plus 5 and upload it to the Arduino board. And with plus 5 we have for each value 2 bytes, so we must have an increase of 10 bytes. And we see here the address F0 and here FA, and A is the hexadecimal number of 10, so this address is 10 bigger than the original address. And for the original one we have here the value of the lower 2 bytes, and for this we have a value which is useless because it points anywhere in the memory where we have no idea what is located on this memory location. So we can summarize: the pointer moves always a multiple of the size of the data structure further. If you have questions, suggestions or other remarks, please write it in the comments below. Remark to the software and the video description. The video description text does not accept the following characters: lower, shift left, bigger, shift right. Therefore, I have replaced these signs with the word lower, bigger, shift L and shift R. So before you compile the software, use the search and replace function and convert the words lower, bigger, shift L and shift R back to the original characters. That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. See you in the next video. Bye bye.